Welcome, everyone. For today's prep, we're going to be looking at, well, probably the scariest topic we're going to be doing in this course. And for an extra special Halloween themed prep video here. And the scary topic here, and honestly, kind of probably one of the hardest topics we're going to do in the course, is constrained optimization. So we're just going to go run through an easier example just to kind of get an overview for how this process is going to work. So a lot of our derivative techniques that we've been learning and a lot of our finding critical numbers and classification methods with first derivative test and second derivative test, they've been kind of leading to this. And that is how to kind of optimize functions. And we're going to be looking at, for our example today, we're going to look at example 1. And this is what's called a constrained optimization problem because we want to find the max value of this two-variable function, q equal to xy, and we have this other equation that says x plus y must be equal to 2. So this is what's called constrained optimization. And the first step for these types of problems is to figure out what we're going to call the objective equation and what we're going to call the constraint equation. So the objective is whatever we want to maximize or minimize. So in this case, our objective, we want to maximize this function q. So that's going to be our objective. That's our objective equation. And the constraint equation, this is some other information, usually an equation, that puts some additional restriction on what our variables can be. And in this case, it's this equation. So if we wanted to just maximize that function q, well, the idea would be, well, just make x and y as big as possible. Well, we can't in terms of this problem because x and y just can't be anything. There's some additional restriction here. There's some constraint on what these variables x and y can be. Whatever we pick, they have to add up, in this case, to 2. So that's the first step for these constrained optimizations. Figure out which equation you want to maximize or minimize. We call that the objective. And then figure out what we call the constraint equation. So in this case, the x plus y equals 2. And usually, in this case, we're given these two equations. We're going to be looking at applied problems where we actually have to kind of cook these equations up for ourselves. And so that's where this kind of gets a little tricky. All right, but for this one, we're given those equations. So once we have those, the second step is to solve our constraint equation for one of the variables, whichever one's easier. So in this case, it really doesn't matter. So let's solve for the usual. So we're going to solve our constraint. We're going to take our constraint equation, which is x plus y equal to 2, and let's just solve this one for y. We'll have occasion sometimes where maybe x is a little easier, but we're just going to solve this one for y. And when we do that, we get y is equal to 2 minus x. Okay, so now step 3, once we've done that, step 3 is to take this result that we just found and plug it into our objective. So we're going to plug it into our objective. And the benefit of doing this is we're going to have a one variable function. So right now we're trying to maximize a two variable function. We're in a Calc 1 course here. So we're used to, we only have the tools to optimize a one variable function. So multivariable functions, that's later on, that's Calc 3. All right, so what are we going to do? We're going to take our objective, which was q equal x times y, and we're going to plug in the result that we just found. So we know that y is equal to 2 minus x. So we're going to replace that y there with 2 minus x. And that's just going to give us a one variable equation, function. Okay. And then once we get to this one variable function, the next step, this is where we're going to unleash our calculus tools. So step 4, this is the optimization part. So this is where we're going to find and classify the critical numbers. So for finding the critical numbers, we know we're going to have to do the first derivative. And then probably for the classification, we'll do our second derivative. So to help us with the derivative process, let's actually multiply this out so we don't have to use product rule. So if we multiply, we get 2x minus 2x squared. Nope, that's not what we get. 2x minus x squared. That's what we get. All right, so this version, be a little easier to differentiate. All right, so let's get to the optimization bit. So step 1, we want to find the critical numbers. All right, so how do we do this? Well, there's 2 ways we can get a critical number. We can either have our derivative be 0, or we can have our derivative be undefined. So let's calculate the derivative. So our derivative here, we'll call it q prime, is going to be 2 minus 2x. And if we're looking for where our derivative is 0 or undefined, well, the undefined, that normally happens, as we've seen, that normally happens when we have division by 0. There's no division here. There's no negative exponents. So for this one, none. All right. Well, what about where our derivative is 0? So let's set our derivative equal to 0. And if we solve that for x, this one's not too bad. We end up with x equals 1. All right, so that's our critical number. And once we have found our critical number, or find all the critical numbers, then the next step is to classify them. And what we're going to do here is our second derivative test. Usually that's the one that's a little bit quicker. So since we have options, when you actually go to classify, state which test you're going to use. So in this case, we're going to use our second derivative test. Okay. So what do we need? Well, we need the second derivative. So let's calculate q double prime. And we go back to our first derivative, differentiate that, we get -2. And the way we perform our second derivative test, we take our critical number, we plug it into that second derivative, and the way this second derivative works is it's just a constant. So no matter what I plug in this case x equals 1, it always returns that same constant. It gives you out that same constant. So we end up with -2 here. And we just want to interpret what that means. So negative second derivative means concave down. To help remember, draw the concave down shape, and that tells us we have a local max at x equals 1. And we just you kind of want to use this classification almost as a check. So we found that we're having a local max at x equals 1. Let's go back up to how the problem's worded. We wanted to maximize this function. So we're not going to have any trick questions or anything where you find that you're getting a local min, but the problem said to maximize. What the problem's instructing you to do should agree with the classification that you come up with. But we do want to see both of these, finding and classifying the critical numbers. All right, so once we've done it, we're just about there. And then the last step is just to make sure that we actually answer the question. So if we pop back up, what did it want us to do? It said find the max value of this function. So we found the x value when this function's maximized, but now we actually have to find the value of the function. So in this case, we just want to make sure. Sometimes it'll say find x and y, or find the dimensions, or things like that. So you just have to read the question and see what it's actually asking for. So in this case, it said find the function value. So we're going to take our x coordinate and we're going to plug that into our one variable function. So we have two versions of our objective. We have the two variable version, but then we also have this one variable version where we used our constraint. So easier to use this one variable version. So if we plug in there, we're going to get q is equal to 2 times 1 minus 1 squared, which is equal to 1. All right. So that's the idea with these constrained optimization problems. And our answer here is this q value of 1. So now we're going to, in class, we'll kind of spice this up a little bit and look at some kind of more complicated constrained optimization problems. And then really where we're going with this is we're going to see some applied problems where we actually have to kind of read through the wording and come up with these equations for ourselves. All right, so we'll see you then. Bye-bye.